Hello everyone, my name is Nitish Jaiswal and I am presenting this project along with my teammate Aishwarya. This project, predicting heart disease using machine learning, was completed as a part of CSCR 6364 under the guidance of Professor David Trott. Our objective was to explore whether we can predict the likelihood of heart disease using simple, non-invasive, survey-based health indicators without actually relying on clinical or imaging data. The dataset was sourced from Kaggle. It contains behavioral and demographic health related information collected from individuals. It includes features like BMI, if the person ever had acne, and the smoking status, if the person drinks alcohol. These kind of features are present in the data set. The set is well structured and suitable for supervised learning tasks. So it's quite likely that we are proceeding with the heart disease prediction. Also, the dataset contains over 4 lakh rows and about 40 columns. Our target variable is binary, so we aim to build a scalable and interpretable early screening tool. The approaches. We experimented with 4 classification models: logistic regression, random forest, decision tree, and XGBoost. Each model was trained on the same features using a stratified 80-20 test train split, and evaluated using consistent metrics, accuracy, precision, recall, and etc. Methodology. Uh, the data set was split into 80-20 set. So we first have to process the data, which involved normalization and encoding of the categorical and so textual data. So you also used EDA plots to better understand the relationship between the different attributes of the dataset. We then trained all the 4 classifiers using the process data set, and then evaluation was done not just based on the accuracy, but more importantly on recall, FN score, and other metrics. So, literature survey. We conducted multiple literature survey where researchers focused on healthcare data sets. And one noteworthy study conducted by a few researchers, uh, they aimed to enhance OPSCC patient management using machine learning. According to them, they're employing techniques such as ensemble learning algorithms like XGBoost and random forest had a more effective impact, or we can say had a more higher accuracy and rather than any other models. Another study we studied was also suggesting that the traditional methods used, including image testing, often proved insufficient, leading the researchers to incorporate machine learning models such as XGBoost, logistic regression, support vector machine, random forest, etc. So we head towards pre-processing. Uh, so we started our data while loading the data in in the Jupyter notebook. We pre-process the data. As you can see, the data we first try to calculate the number of percent of how much data is missing. And we decided the threshold if any column has more than 40% of missing values, we'll delete the column. But it turned out that all the columns were less than the threshold, so we used the basic techniques like of median and mode to fill out the missing values in the data. We used median to fill out the missing values in numerical data columns and mode to fill out the categorical data set with missing values. Moving on next to uh, exploratory data analysis, we made different charts plotting relationship across different attributes of the data set. The first is heart attack distribution across smoker status. Uh, Among everyday smokers, about 8.3% reported have a heart attack. Those who smoke only some days have a lower heart attack rate at 6.8%, while former smokers showed 8.2% of um, a heart attack rate. In contrast, individuals who had never smoked had a heart attack rate of only 3.7%. This shows that both current and former smokers carry a significantly higher risk compared to those who never smoked. Next, moving on to stroke history versus heart attack. We analyzed stroke history. Among individuals who had previously suffered a stroke, 25% also had a heart attack. Meanwhile, those without a stroke history just showed a much lower heart attack rate of just 4.6%. This confirms stroke as a strong predictive comorbidity for cardiovascular issues. The third one is depressive disorders and heart disease relationships. Mental health also appears to be a meaningful factor. Of the individuals with diagnosed with a depressive disorder, 6.5% had experienced a heart attack. Among those without depression, that number was 5.2%. Although the difference was not much, but it might suggest that emotional well-being plays somewhat role in your cardiovascular health. Moving on to the next chart, age category and heart disease. Lastly, we look at how heart attack varies with age. In younger groups like 18 to 24, the incidence was extremely low, like 0.38%. As we move higher up the age, it significantly increased. Like in the ages of 45 to 49, it was about 2.5%. Ages 60 to 64, it was nearly 6%. And at the age of 75 to 79, it was 11%. And those older than 80, the heart attack rate increases to 14% approximately. Clearly, the older individuals is more susceptible they are to heart the more susceptible they are to heart disease, making age one of the most critical factors. Moving on to the pre-processing, now we have numerical columns and categorical columns. So in our machine learning, we cannot use directly categorical columns. So we have two encoding methods, label encoder and one-hot encoding. So how label encoder works is it encodes each category and assigns it as a new number. Like if you have sex male and female, so it will assign male as 0, female as 1. But the problem with this methodology is machine learning, as you know, is all about weights and numbers. So it creates some kind of bias in the model when different attributes are numbered differently. So here, the higher number will get more bias rather than the lower number. So we went forward with one hot encoding. So what one hot encoding does is it creates new column for each attribute, assigning 0 if the column does not represent that value, and 1 if the column has contains the value. I mean, if the column like for example, if it's male and female, so it will create two more columns like sex underscore male, sex underscore female. If the person is male, then it will tick mark male as 1 and female as 0 in that particular case. So here's how it works. So in this way, we encoded all our categorical columns and tried to make out a physic correlation matrix. So when we made a correlation matrix, we uh, tried to uh, get the most top 30 values which were correlated with our target column, that is the had heart attack. We had some data like had agni and had stoked or more inclined. Moving on, we then proceeded with modeling, and we successfully modeled all the four models: logistic regression, random forest, XGBoost, and decision tree. We generated all the classification report, and according to the report, we decided that the XGBoost model was the best fit for our data set, and it might be the most accurate and perfect model for the data set we are proceeding with, for the target variable we are proceeding with. But later, as we plotted the confusion matrix and ROC curve of the model, we realized that this might not be the best model because our data set is highly skewed, as it contains more than 80,000 entries of one particular attribute. Like if not, it had not a heart attack is having more than 80,000 attributes, and the positive the positive label, like yes, if the patient had heart attack, had only about 8,000 or 5,000 attributes. So the data set was highly skewed. So we plotted all the ROC curve and confusion matrix of all the models, and it turned out that the random forest was the best fit for our model. As precision and recall and accuracy, considering all these factors, we went forward with the random forest model. We then proceeded to get the top 20 important features which were uh, supporting our model. And it turned out that the, the attributes, if the patient had agnia, BMI, the weight, the height, the number of hours the patient sleeps, physical health days, mental health days, if the patient had stroke, and of factors like the smoke, if the patient was a former smoker, alcohol drinker. So here's the plotted graph of the top 20 features according to their importance. Now moving on to final results and conclusion. The model we selected was random forest. The overall accuracy was 94.7%, high but majorly driven by the majority class. As our data set was skewed, 94% of the class 0, we had like 88,000 rows of class 0, and 6%, 5,000 of positive classes. This makes the data set highly imbalanced, and our model is not that quite good in other guessing the other class. The top features supporting the model are head agnia, BMI, weight, height, and sleep hours. Here, thank you so much.